to organise the President's address for this afternoon. So hence we're in this lecture today, so I'm pleased you all made it. So format is we have 3 talks from the department before the break, then a tea and coffee break, and then we'll listen to Barbara Lane from Arup after the break. So our first speaker is Amir Kadiric. Amir.
Thank you, Peter. Okay, good afternoon all, and thank you very much for being all, particularly because there's this other secondary event going on at the same time. I'm Amir Kadiric. I work in the tribology group in the Department of Mechanical Engineering here at Imperial College. And as tribologists, one of our major areas of interest are the mechanisms of surface damage in rolling sliding contacts. And today I will talk about one type of surface damage, arguably the most significant one, that of rolling contact fatigue. Rolling contact fatigue manifests itself as pits, cracks, and spalls on the surface of affected component, hence the imaginative second part of my title. But some of you in the audience might recognize a subtle nod to one of our collaborators who have been instrumental in helping us develop some of the experimental methods that I'll be showing you later on. I'd also like to acknowledge all the help and support from current and past PhD students, some of whom are listed here, but by no means all. So let's start by talking about rolling contact fatigue in general. What is it? Well, as the name suggests, it's a fatigue type of damage, therefore requires some cyclic stresses. And in this case, the cyclic stresses come from repetitive overrolling of the contact. For example, during gear meshing or overrolling of a rolling element over a ring in a rolling element bearing, or indeed a wheel over a rail. It is often the life-limiting failure mode in highly stressed rolling sliding contacts, such as those in bearings, gears, cams, and so on. Considered to consist of 2 stages. First, you have some damage accumulation period, which eventually results in initiation of a crack. And then that crack propagates, in this case across the surface, it can be subsurface, and creates a pit on the surface. Once you've created that pit, the damage propagates very fast until the component has failed. Traditionally, it's this crack initiation phase that's been considered as the life dominant, and propagation phase has been assumed to be negligible in length. As I say, surface and subsurface initiated. Historically, subsurface initiated rolling contact fatigue was more significant because the crack started at subsurface non-metallic inclusions. However, with steels getting cleaner and some other developments in tribology that changed the contact conditions, we are seeing that modern machine surface-initiated rolling contact fatigue is actually much more significant. It manifests itself in 2 major modes. One is pitting, where you get pits of the size of the order of the contact size, hundreds microns to millimeters, such as in this bearing, or micropitting, as the name suggests, where the pits are much smaller, size in tens of microns. Now, all very nice. Why are we interested? Why do we bother with this? Well, if you consider that there are about 50 billion, apparently, rolling element bearings in the world, almost every single mechanical system has them. There are many gears, many miles of rails. You start realizing that actually understanding the mechanisms of rolling contact fatigue and our ability to predict it can have an impact on a vast range of mechanical systems in terms of operational costs, so reducing the maintenance cost and downtime. And I've just picked one topical example, wind turbine gearboxes. Failures in these gearboxes are reported to be responsible for the largest proportion of wind turbine downtime. And 70 to 80%, depending on what you read, of those gearbox failures are due to bearings in one of the stages of the gearbox. Here I have some data from a particular database from one of the major gearbox manufacturers that shows that the actual service life of these bearings is about 6 months. That's L10 life, so a life by which you would expect 10% of your components to fail. Whereas actually the design life was 24 years. That's a factor of 50. It's not always 50, it depends on which database you look at, but you can see the significance of it. If you cut those bearings up, in the subsurface, you see this nice looking, what we call white etching cracks, so widespread crack networks decorated by this microstructurally changed steel that appears white once you etch it and look at it under an optical microscope. So the obvious conclusion is we have these strange cracks, we have these early failures, these cracks must be causing the failures. We're doing a lot of research in this area, we don't have time to talk about it, but it turns out that actually they're not directly related to each other, but both are caused by a third factor, a particular stress sequence in time. That's one of our major ongoing areas of research. Another aspect where rolling contact fatigue is important is reliability of systems, particularly safety critical systems. Helicopters are a good example. There's a nice video which I can't play because it will take too long, released by Airbus, so I urge you to look at it. It's under what they call Creative Commons Attribution License, so you can look at it and share it, where the Super Puma that crashed in Norway in 2016 was found to crash due to rolling contact fatigue failure on the planet gears in the main gearbox of the helicopter. As ex-colleague of mine, Andy Olver, used to say, helicopter is just a flying gearbox. There you see one of the cracks in the planet gear from that video, and you will see later on in some of our research we generate something that looks very, very similar to this. Other obvious examples of safety critical systems, the Hadfield derailment was caused by rolling contact fatigue in rails, and nowadays we are working in introducing gearbox in normal jet engines, let's say, to have geared turbofan engines in order to slow down the fan and improve the efficiency of aviation turbines. And of course, safety is critical there too. There are a couple of things going on in the world of tribology that means that, luckily, the interest in rolling contact fatigue is increasing rather than decreasing. So I'll just say a couple of things about those trends. So here I pinched a slide from our colleagues at SKF that shows a given bearing with a given load carrying capability from 1950s to about now, a decade ago. You can see that the weight of it is reduced by a factor of 3. The load carrying capability is the same, so the stresses have gone up. What that means is that the contacts are having to deal with much larger stresses. There's much more metal-to-metal contact. The other important trend is reduction of viscosity of lubricating oils. In engines and gearboxes and so on, we are trying to use low viscosity oils in order to reduce hydrodynamic losses, churning losses, reduce friction. But of course, you can see this is an example from our engine oil in passenger cars in the US from Infineon. And you can see in 80s, this orange bit is 10W40, quite viscous oil, and that proportion is decreasing, where that 5W30 is increasing. Who knows where we go, 0W20 and so on. So oils are getting less and less viscous. Both of those trends mean that our lubricating films, which we rely on for protecting the surfaces when they rub against each other, are dropping significantly in time. That means more metal-to-metal contact, and that means, I won't play the video, but that's, it's not very, you can't see it very well from up there. That means that asperity interaction is becoming a major contributor to failure modes of surface-initiated fatigue. So how do we deal with this? That particular example of a helicopter, one of the solutions was to decrease the servicing, the inspection intervals. And to do that, what they've done is use some old equations to predict the probability of failure, the ln 1 over s, related to the stress in the subsurface to some power c. C is a very large power, 9 to 12, so very stress sensitive. Life to the power e, E is the variable slope, and times the stress volume. In 1980s, this was improved by Ioannidis and Harris by actually discretizing this volume. So you estimate the probability of failure in each of the cells, add them all up, and also introduction of the fatigue limit. Now, Ioannidis, he's an ex-colleague and a good friend of mine, and he's supposed to be here, but he called 15 minutes ago saying he can't make it because he's fallen ill, which is not so bad because I'm about to say some things about his theory that he might not appreciate. So it's great, and it's widely used, and it's in ISO standards, and we do need it. However, it does have its deficiencies. So the obvious one is this is a Weibull slope. And if you look at Weibull statistics, to get any statistically significant numbers, you need a lot of failures to plot the Weibull slope to get it accurate. So it's expensive, time-consuming. A couple of other problems. It does not account for the sequence of stresses. So whether you have a high stress in the beginning, moderate stress, high stress at the end, like we did in those wind turbines, and that's what caused our early failure, this theory will not account for it. Yeah, lots of other fatigue theories don't account for it, so it's not a fault in itself. Also, it doesn't actually include any understanding of crack initiation and propagation. It's an empirical model. And that effectively means that we assume the initiation is the dominant phase. So once you initiate a crack, it will give you a failure. That, however, means that it can't be used for something we call predictions remaining useful life. So if you have a component, helicopter gearbox, and you detected a fault, you're really interested in predicting how much longer you have until that component fails. Well, you can't do that with this. you need to understand something about crack propagation and the remaining useful lifetime. And that's becoming more important with sensor development and machine learning tools used for condition monitoring. So can we do better? Well, we try, but it's not easy because there are rolling contact fatigue slightly different from classical fatigue, and I've listed some factors here. I'm not going to talk about all of them. Stress system is multi-axial, non-proportional. If you include the roughness of the surfaces, actually it's random as well, because the roughness is changing during the rubbing process, particularly if you're talking about fatigue in the last millions and millions of cycles. You have presence of lubricant, which can create additional factors, such as the entrapment of lubricant in the surface breaking crack, which can accelerate propagation. Crack closure and rubbing, which means that it's very difficult to work out stress intensity factors, as you will see later. And the post-failure damage is significant, so it's actually difficult to establish root causes of the failures. So it's difficult to study, but we try. What do we do? Well, three things, really. Number one is trying to gain some understanding, improved understanding, by using an experimental methodology. And what do we need to study this experimentally? Well, number one thing, really, is we need to accumulate contact cycles at a very fast rate because we're lazy. We're not going to sit there for weeks waiting for this failure. So that's number one. The second thing, rather than testing to pitting when the component has failed, what we really want to do is look at shorter cracks and how they actually progress to cause that pit, because it's the only way we're going to be able to predict that remaining useful lifetime. And then we want to control contact conditions, so some of these might make sense to you, slide roll ratio, contact pressure. Measure friction, if possible, control it by changing the conditions, control surface roughness as much as possible, and so on and so on. So that gives us some understanding. Then we combine that with some numerical models, and we have extensive numerical models of the contact as well, to obtain some knowledge of driving mechanisms. And the third step is, once we have these driving mechanisms, can we really come up with these better predictive tools and better design criteria so that we can improve our maintenance strategies? So, experiments, number one. This is what we use to study rolling contact fatigue. A triple disc contact fatigue rig, or often referred to as PCS Instruments MPR rig, who are the manufacturers of the current version. And now you might see the significance of the pits, cracks, and spalls. We have a triple contact arrangement here. So we have 3 discs and a roller in the middle. This roller obviously sees 3 contact cycles per revolution. We can generate about 1.1 million contact cycles at a high speed. A couple of other things that we have done to these rigs that you can't buy. We have custom-made crack sensors on these rigs, which basically allow us to identify cracks at a very early stage, 50 to 100 microns. We control the temperatures, so we control the film thicknesses. The discs and the roller are driven independently, so we can control the amount of sliding to rolling, which is quite important if you're studying gears, if you're studying bearings, if you're studying cams, and so on. So let's look at some results we've generated on this. Plenty of pictures, because I think it's much more suitable than equations for this. So let's look at the pictures. So here's an example of a crack that we identified relatively early, not as early as usual, but at least you can see it here. And then follow this propagation. A couple of interesting things here. Here, the crack is assuming that V shape, which is very characteristic of surface-initiated rolling contact fatigue. It then propagates to the sides and into the surface until you get a secondary crack breaking the surface here. The propagation is against the direction of friction. And if you look here, this is a serial sectioning using FIB of an earlier crack than that. It assumes this angle of about 30 degrees to the surface. And there's some interesting things here, interaction with the microstructure and so on, that we can't look at with carbides and so on. So we seem to be generating damage that's representative of real components. Well, let's take one of those big cracks. We can control the propagation rates now using this methodology, so we can propagate them long or short or whatever. And here's a cross-section of that very long surface crack, and you can see some interesting things. It's gone quite deep into the subsurface, similar to that helicopter one you saw earlier. We've got some zigzagging here. You have an angle that's changed after the initial initiation of the surface. If you look in more detail, you can see secondary cracks coming up to the surface. It is those cracks that give you the initial failure. So we really need to understand this as well as this to actually predict propagation and failure. If you zoom even further, you can see that these cracks actually appear to be affected by microstructure. They're all quite short, if you think about classical fatigue, because we're talking hundreds of microns here. You also see some debris, which means that the crack faces have been rubbing. This is quite important because it suggests that the friction between the crack faces is important. It can affect the stress intensity factors of the crack tip, so we need to account for it. So we basically measure crack propagation rates because we follow those cracks. And here's a plot of some crack propagation rates. Here's a normalized life, crack length. We identify the cracks, I call the first detection, not initiation, because when is a crack, so I'm just going to call it first detection. Very early, 15% of life. Most of the life is consumed by the stable propagation phase, in contrast to what's assumed in the rolling contact fatigue life theories. And eventually, they get quite long and propagate, because you can see, if you had methods to detect the crack only here, of course you would assume this doesn't matter, and it's all about initiation, and you get failure very quickly. But if you can see them here, it means the propagation is more important. Because we have crack lengths at different cycles, what we can do, we call this phase 1 and phase 2, just like you do in classical fatigue. What we can do is plot crack propagation rates against something that resembles a stress intensity factors. As I said, because of the complications that I mentioned earlier, we can't work out yet accurate stress intensity factors, although we are working on that. So we plotted surface pressure, pure contact pressure, times root crack length. And you see some interesting things here. Here, the crack propagation rate is slowing for the short cracks. Here, it's actually quite linear. So we can even write something that resembles a Paris-type law with exponents and so on. The exponents are not important. It's the first time this was done for rolling contact fatigue, relating propagation rates to pressures, because it allows you to actually predict how long this has got to last. But it does also mean that it appears we can apply linear elastic fracture mechanics to rolling contact fatigue, which is actually a major area of research for us in the future. A couple of slides on the other manifestation of rolling contact fatigue, and that's micropitting, where we have very small pits as opposed to macro pits, and you say, why do I care? It's 10 microns. But if you let it progress, you lose half of the gear tooth, as you can see there. And we can observe this progression of micropitting on the surface. I'm just going to play this for you. The reason this occurs is because of interaction of asperities. This is actually in our experiment. You can see the asperities interacting with each other. That creates stress history. If you're unlucky to sit on top of one of those, this is the kind of stresses you will experience depending on the slide-roll ratio. And of course, that gives you some accumulation of fatigue damage on asperity cycle level. And if you add other things to that model, such as lubrication and wear, which is important because it's a competing mode, we can compare our model predictions to our experiments at different conditions. And it's not too bad. 2% damaged area, 4% predicted, 10%, 11%. We're working on this in more detail. So I'll wrap up by saying contact fatigue appears to be important because it affects such a vast range of systems. And I think we're making some progress using some latest experimental techniques and numerical models. And in longer term, what we really want to do is use that understanding to provide better predictions and hence reduce the maintenance and downtime costs of mechanical systems. I'd like to thank some of our sponsors, but that's it from me. Thank you very much.
Thanks, Amir. We're slightly tight on time, so I'm going to suggest that we hold questions, and Amir will be around at the break after these talks. Thanks.
Okay, thanks.
So, our next speaker is from a different topic, is Stelios Rigopoulos, who will talk about combustion, a prediction thereof.
Okay. So, thank you very much, Peter. Actually, combustion is only a small part of what I will speak about. In fact, what I want to speak about is a range of problems, some of which you see here, and they are quite wide-ranging. This is the one most relevant to combustion, which is soot formation soot emissions, which are formed in aircraft engines, in IC engines, and so on. But you see some very different problems also here. Here we have crystals formed. Here we have some nanoparticles. Here we have a cloud, which we've all seen. And here we have an oil pipeline that is clogged by certain compound called asphaltins. And all these things have something in common. which I will explain, and I will speak also about a method which unifies all these problems and on which I am working, which is the population balance modeling. So let's see. First of all, it may not be immediately apparent what all these things have in common, but I will tell you to get started. What they have in common is that in all of these things, we have a population of particles. In some of them, it's apparent, like here or here, but it's not so apparent in the cloud or in the pipeline. But in all of them, there are actually particles that interact and form something. And the particle size distribution of these things is very important for various reasons. Let's see, for instance, let's start from the case of soot. So soot is a major problem for aircraft engines in particular, also for IC engines. And the reason is because it's very harmful to human health. And here you see a TEM from experiments by my collaborator, Ben Williams at Oxford. And what you can see here is that we have not just a unique kind of soot particles, but a very wide range of particles. Now, different particles of different sizes have different impact on human health. You can see, for instance, that the most dangerous ones are actually the smallest ones because they can penetrate inside the lungs. And the question that we want to ask here is, can we link the soot particle size distribution with what goes on inside the flame, what you see here, all these complex things that happen inside the flame? If we could do that, then we could design and improve our engines, for example, in order to produce, or rather to mitigate soot particles of a certain size. Now here we see some different kind of particles, which are now good particles. These are nanoparticles that can be used as materials in batteries. These are experiments by a group I collaborate with in China. And again, here the question is, can we link the properties of these nanoparticles with the design of the process? If we could do that, then we could design our process in such a way as to produce tailor-made nanoparticles for a particular reason, for a particular purpose. For the cloud, it's not so obvious, the link, but actually the cloud is composed of many small droplets. And what you see actually here between the droplets is some small particles, which are actually soot particles in this case. These aerosol particles, they can be soot, and they can also other atmospheric aerosols. They're very important because droplets nucleate on these things, and then droplets interact and coagulate, and this is how clouds are formed. So the question here is, can we link how droplets grow larger, how they interact with aerosol particles, and ultimately how rain falls? So these are problems also of environmental interest, not just engineering. And this is another example which takes me back to my PhD, actually, which was on crystallization. And here we see some crystals formed in a liquid phase. This process is very important in pharmaceuticals manufacturing. And again, we want to make our crystalline product have a certain particle size distribution in order to be able to deliver it to the human body. And the question is, again, whether we can link the crystal properties with the process conditions. Okay, so let us try to formalize these things. To formulate some more in-depth research questions here. So the first question is, how can we link the particle size distribution that results in all these processes to the fundamental aerosol processes that determine it? And I will speak in a moment what are these processes, but things like growth, nucleation, coagulation, and so on. Secondly, all these problems that I showed to you occur within a flow field. So how do we model aerosol processes that take place in a flow field like this? And a related question, how do aerosol processes interact with turbulence? As you can see here, this is a turbulent flame, a simulation of a turbulent flame, and you see that we get all these complicated structures. All these things have a profound effect on aerosol processes. And then, if we could understand these things, can we use this knowledge to build computational models to predict the process outcome? In other words, whether we're going to get particles like this or particles like this. And ultimately, the question, of course, is, can we solve engineering and environmental problems with this approach? So these are the research questions. Now, I will summarize here what we have done in my group very briefly, and then I'm going to expand on all these things. So first of all, the unifying concept between all these things is the so-called population balance equation, which I will explain in a moment. Now, the problem with this equation, as you will see, is that it's very difficult to solve it. It's very challenging because we have to accommodate very different phenomena in it. Phenomena like surface growth, coagulation. These are phenomena that have a very different physical and also mathematical description. And so it's challenging to develop methods, and we have developed some new methods for this equation, about which I'm going to speak. Now, having had these methods, how can we couple this with fluid dynamics? This is very difficult also, and I must say that for a long time, the community believed that this would be a too expensive problem, computationally expensive problem. So the approach generally was to simplify either the fluid dynamics aspect of it or the population balance aspect of it. Simplifying fluid dynamics means to consider the system as either fully mixed or a network of fully mixed zones. Simplifying population dynamics means to consider it, for example, as monodispersed. But what we have done is to couple the population balance with CFD. And we've done this for RANS, LES, and even DNS recently. And we have shown that at least with these new methods that we developed, it's possible to do this. It's computationally feasible. That's one of the main messages I want to give today. And then, even more challenging problem is the population balance in turbulent flow. How do turbulence interact with aerosol dynamics? This was an unresolved issue for a long time, and we have proposed a method to study this, but also to model the effect of turbulence on the population balance, the so-called population balance equation probability density function method, which I also will explain. And finally, we have applied it to a number of systems, which I will show in the end. Okay, so now, first of all, let's see what exactly is the population balance equation. So it's an equation that provides a link between micro, meso, and macro scales. So what do we mean by this? All the phenomena that give rise to the development of an aerosol population start from the micro scale. Things like molecules coagulating into nanoaggregates and then into clusters and so on. One could obtain some insight into these things with things like molecular simulations. But what we actually experience in engineering or in environmental problem is a macro scale, what you see here, which is a distribution. So if we take a measurement of an aerosol system, we're going to measure a distribution of particles. We're not going to see all these things. All the systems are huge. A gas turbine is very big. It's possible to simulate it with molecular dynamics. And the link between the microscale and the macroscale is the population balance, which involves this phenomena that occur at the mesoscale, phenomena like nucleation, growth, aggregation of particles and breakage of particles, which give rise to this population. And within these things, we can provide in the form of constitutive equations inside that we have from the microscale. So we can link these scales. Now, here is a population balance equation. I will give a brief explanation of the terms. There are many forms, but this is a basic form of it. So here we have the accumulation term. And what this describes is how the particle size distribution evolves in time. How it's, for example, it might be like this at one time instance, and then the next time instance, it is like this. Then we have this term, which describes any kind of continuous change in particle size, like, for example, particle surface growth or condensation on the particle surface or evaporation. All of these things what they have in common is that we have a particle which is changing continuously in size. Continuous is important. You'll see in a moment why. Then we have nucleation here, which is formation of new particles. And then we have two terms on the right-hand side, which describe processes that are not continuous, but rather what is called jump processes. They're processes like coagulation, where two particles combine and form a bigger particle, which means that two particles are going to disappear from 2 points in the distribution, and then they will reappear somewhere else. And as you can see, one of the challenges with this equation is that it is a so-called integral differential equation. It involves both integrals and derivatives. The reason is because we have to accommodate both continuous processes like surface growth and evaporation and jump processes like this. And the reason we need these integrals is because we have to account for all possible pairs of particles that can combine and form a particle at a certain size. Okay, now, this is difficult enough, but when we have this occurring within a flow field, we're not going to have just one distribution, but a different distribution at every point in space. So if this is a simulation of a flame, we'll have actually different particle size distributions at different locations along, let's say, the axis, distributions at a different time. This is why we need to couple the population balance equation, or PB for short, with fluid dynamics. But there is also another reason which is even more profound. And the other reason is that fluid flow, as I would say, sets the stage for all this phenomena to happen. This is exemplified by this case. This is a simulation we did of precipitation of two chemicals to form crystals in the liquid phase. And what you see here is that we have one chemical coming from here and another one coming from here. Now, the mixing and the turbulence around this zone determines the local concentrations and the local rates of phenomena like nucleation and growth. So you see here that we have a different distribution of the nucleation rate and of the growth rate. Now, the balance between these processes is going to determine the kind of product that we get, because if we have a lot of nucleation, we form a lot of small particles, and then these small particles consume very quickly the reactants, and then you get a lot of small particles and very narrow distribution. If you have a balance more leaning towards growth, you're going to get a lot of fewer seeds, and which will grow to bigger particles. So if you can control this, if you can set the stage by somehow controlling the fluid dynamics, you could control what particle size distribution you're going to get at the end. And finally, so I think I have made the point so far that we need to solve the population balance within a flow field. So now I'm going to start to tell you how we have addressed these challenges. So as I said, first of all, the first problem that we have to address is the numerical solution of the population balance. We need to use numerical solutions because it's a very complex equation. Analytical solutions are only for benchmarking such cases. And the first innovation we did here was an adaptive grid method which tries to resolve the following problem. Typically, in an aerosol problem, you have a range of particle sizes that could be up to, let's say, 3 orders of magnitude in diameter, 9 orders of magnitude in volume. And we usually need volume as an independent variable to model coagulation. This means that we need to use a non-uniform grid to cover all this range. And as the particle size distribution will move from smaller sizes to bigger sizes, as happens in growth-dominated problems, it's impossible to capture this with a fixed grid. So what we developed is an adaptive grid that will move the nodes in the particle size domain in order to follow the distribution around and be able to model a problem like a problem dominated by growth. This means that we also need few grid nodes and CPU efficiency, which is very important in this. The other method, which is a very recent development, and I'm very excited to talk about, is a conservative finite volume method, which tries to address coagulation-dominated problems. So the problem, the problem of modeling coagulation with the population balance is that, again, you have a non-uniform grid, and when particles combine and disappear from some part of the domain, they form particles that usually do not lie on any of your existing grid points. Previous methods try to modify the distribution in some way so as to conserve some overall properties of the distribution, like the total mass, for example. But in doing so, they're compromising the accuracy of the distribution. What we developed is a method that is conservative. It conserves absolutely the mass, which is the important invariant in coagulation, but at the same time, it gives an accurate prediction of the distribution and is also very efficient in terms of CPU time. Here you see also some comparisons of our method with analytical solutions. Now, when we coupled all this with fluid dynamics, we simulated here a laminar shooting flame, and what you can see is here is a simulation of the shooting flame, and with a modest number of grid points, we can get an accurate solution very close to the experiment. But most important here, the part taken by the population balance in the overall simulation is less than 10% of the total CPU time of the coupled CFD-PB simulation. So we have shown that it is feasible to couple the population balance with CFD. This is something that was long believed to be too computationally expensive, and you can see here the distribution evolving at different stations in the flame. Now, even bigger challenge is what happens when we have a turbulent flow. Now, what is the problem with turbulence? So first of all, aerosol particles like soot are being formed by some reaction in the gas phase, by some precursors. And these precursors, as you can see, are subject to random fluctuations here. So this means that we're going to have fluctuating nucleation and growth rates, which will profoundly affect what is going to happen. Secondly, we're going to have random fluctuations in the particle concentration as well. And this will affect the coagulation rate, which is, again, which is proportional to products of number densities of different sizes. All these fluctuations have some effect in the distribution, which is not accounted for. The way that we do this is with the so-called population balance probability density function method. And what we do here is we simulate our flow, our turbulent flow, with runs or even large eddy simulation. This is a large eddy simulation here. And we're actually having an ensemble of distributions at every point, which is what would happen in a real situation. If you actually sample the distribution in a turbulent flow, you would find a different distribution in every experiment because of the effect of turbulent fluctuations. So what you're going to have is effectively a distribution of distributions. So our method simulates the effect of turbulence on the population balance by having an ensemble of these distributions. And we have coupled this with LES and simulated a turbulence shooting flame with LES. I must say that this was the first study of its kind, the first study that predicted the soot particle size distribution with large eddy simulation. And even here, even though we have to simulate the whole ensemble of distributions, the time taken by the population balance was less than 30% of the total CPU time. I think I have to speed up. These are some samples from our latest work. Here we have coupled the population balance with direct numerical simulation. It's a collaboration with Dr. George Papadakis from Aeronautics. And what we want to do here is to probe further into the interaction of turbulence and aerosol processes and understand what happens when the time scales of mixing and reaction overlap, how this interaction of time scales gives rise to unique phenomena in the aerosol phase and ultimately help us to build better models. And the final example here is a collaboration with both Dr. Papadakis and Dr. Janet Wong, is the clogging of pipelines due to asphaltene depositions. Now, asphaltene is a compound that has a very similar structure to soot. And what happens is that due to aggregation of asphaltene, you get these structures that clog the pipe and can cost millions because one would have to stop the operation and clean the pipe. Here are some of our simulations where we try to simulate the particle size distribution, and here are the fluid dynamics. And what we want is to be able to anticipate the formation of asphaltene and control it before it can deposit on the walls. So I think that I have to conclude here. So what I have tried to say is that, first of all, that the population balance approach can provide a unified description of a wide range of problems like aerosols, nanoparticles, crystals, cloud formation, fouling. We tried to show with our research that the numerical solution of the PBA in this coupling with CFD is computationally feasible. It can be done. We developed an approach for addressing the problem of the population balance in turbulent flow, and applications of the coupled CFD-PBA simulations have great potential for the future. And I have to acknowledge also my academic collaborators, PhD students who contributed to this work, and our research sponsors. So thank you very much.
Thank you, Stelios. I think again, in the interest of time, we'll press on to the next talk. You can speak to Stelios in the break if you'd like to ask any questions. Thank you. So our third and final speaker before the break is Ravi Vaidyanathan, who will talk about robotics.
Let me just take 1 second here to make sure. All right. Thanks, Peter. For those of you who don't know me, my name is Ravi Vaidyanathan. My title here is Senior Lecturer in Biomechatronics. I've been a little glib in describing that as no one really knows what biomechatronics means. So the way I look at it, I get to come into work each day and do whatever I want. So with the length of the talk here, I also should say at the outset, I understand the last talk before refreshments its merits are usually judged on its reticence. So I will do my best to give you a quick overview of the kind of work my lab is doing right now. We won't get too much into the modeling details, but I'll hopefully show you some of the applications, which you can see where the research is going and what we're trying to do that's interesting. So the first thing I'm going to do, since no one knows what this means, I thought I'd start with an example that describes it. The first thing I need to say is this is an experiment I had nothing whatsoever to do with. Okay? This was done by Professor Bob Full at the University of Berkeley. It was done when I was a student, but I was lucky enough that my PhD supervisor knew Bob, and we talked about this experiment, and it really changed the way I looked at things as a student, kind of directed the field that I think is now the basis for my lab. So what Bob did, he took a cockroach and he superglued a cannon to its back. I am speaking literally, I'm not making an analogy. Okay, that is a cockroach. It is running towards you. That is a cannon on its back. It's glued on there. That cannon is firing a bolt. All right, so let's say this is the cockroach. It's running right at you. There's a cannon on the bolt. The cannon fires that way. What's going to happen to the cockroach? Be pushed this way. Okay, so why would someone be demented enough to do this? Unless they just lived in an infested apartment and went mad. So what Bob was actually doing, he was trying to study balancing in the robot. Okay, balance in robots is a huge issue today. Walking across the room with a robot that walks across the room, not a big deal. Robot walking up the stairs, really not a big deal. Robot that walks across the room and walks up the stairs. Still quite a challenge today. How do we handle those transitions? So cockroaches do that without much trouble. So what Bob was actually studying was how does this insect balance? How does it maintain its posture stability in the presence of disturbances? Now, the reason he was using a cannon to perturb it was because the cockroach's central nervous system, my own PhD was modeling the cockroach's escape response when it dodges predators. It can dodge a predator in about 14 milliseconds. It dodges based on wind. Feel wind blowing to towards the cockroach, a predator lunging. If it's moving, it takes about 14 milliseconds from the onset of wind to the control of a dodging maneuver. And that dodging maneuver controls about 49 degrees of freedom. So, and if the cockroach is standing still, it takes about 60 milliseconds. Now, we've probably experienced, imagine if you're sitting down or if you're standing still, you start running, it takes you a little while, your muscles are a little sluggish when they get going. So let's, simplistically, though, it's really not that bad. Let's take that 60 milliseconds response when it's standing still and the 14 when it's moving, and let's set aside 46 milliseconds, the time it takes to fire up the muscles, and take 14 milliseconds as the time from stimulus to the time it's going to dodge. Okay? Now, that's a pretty fast nervous system on our standards. Bob was trying to perturb the cockroach faster, and let's assume that's about the fastest it's going to move because it's a predatory survival response. So Bob was trying to perturb it in less than 10 milliseconds because if he perturbed it slower than the nervous system could react, he wouldn't see the whole reaction. And that's why he used a cannon. Okay? So we're expecting to see some kind of visible adjustment to this cannon. But it imparts a sharp normal force. A lot of calculations went into figuring out just how that normal force right. It was less than 10 milliseconds, faster than the central nervous system should be able to react. But his postdoc, Devin Gindrich, actually said, based on experiment, quote, that cockroach didn't break stride. Okay, so unless we're wrong about the nervous system reacting in less than 10 milliseconds, a lot of modeling went into that, including my own PhD, so I don't think that's wrong. Why didn't we see a more visible reaction from the cockroach when we perturbed it that fast? And the reason is because there's a host of mechanical properties within the cockroach, within muscles. Muscles, for those of you, it's something called the Hill muscle model, goes back to the 1920s. Muscles act like springs and dampers, but the key thing is the stiffness and damping parameters change in those. There's a lot of passive stiffness in the exoskeleton, stiffness in ligaments, joints. All of that makes a very sophisticated mechanical system that acts to stabilize the insect. So even though its nervous system cannot react that quickly, it still rejects disturbances and maintains balances far over the speed that its nervous system can react. And then when the nervous system actually does kick in, there's a synergy between the two. And so essentially the mechanical properties of the system augment the neurological control. So the term we call it is the so-called neuromechanical system because that synergy between the mechanics and the neurological control. And then if I was to take that one step further, what I call biomechatronics, then if we take mechatronics as looking at electromechanical systems, well, in your body, of course, every nerve cell is an RC circuit. your muscles are actuators, your skeletal structure is your skeletal's mechanical structure. How do all those interact together? And that's what I call biomechatronics. So I hope I didn't torpedo by getting to do whatever I want to do each morning at work. But that's how I think of the field, and that's roughly what I mean when I say biomechatronics. So that was the central nervous. This is another cockroach. Again, I studied cockroaches for my PhD, so I feel the need to inflict them on people. This is a cockroach climbing up an incline. This is done in the lab of Professor Roy Ritzman. I worked under him when I was a PhD student. I was bouncing between mechanical engineering and neuroscience. That cockroach is climbing up a 45-degree incline, okay? If you've had the misfortune of seeing a lot of these things run about, you know they go a lot faster than that. This is very, very slowed down. So it's happily wandering up and hitting that 45-degree incline. It's doing it seamlessly, okay? And it would be going a lot, again, it's going a lot faster than my video is showing it. That's a 250 hertz video. So, well, think about it. Right now, there's not a legged robot in the world, or even imagine someone with a prosthetic leg who would handle an incline like that very easily. We aren't really there yet. Even a robot that could do it at all, maybe a wheeled robot with a nice low center of gravity that could maintain friction on it, that could do it, but then it couldn't climb anything. So the cockroach does. So this might be interesting. Now this is that same species of cockroach climbing that same incline. You'll have to take my word for it, though. It is now climbing without a brain. Okay? That cockroach, for all intents and purposes, has been decapitated. The nerves in the back of its head have been cut, so the brain is not talking to the body. And the body is still going up there. So again, if anyone know what a decapitated cockroach is most likely to die of? Starvation. Okay? So that it is getting up. It is getting farther than any robot we really know of today, but it does eventually have some problems. So what is going on, actually, when from the brain down to the body? How do we look at that? How do we model that? And how do we capture that in robotic systems? That's the big picture. I will show, this is a robot that I'd worked on several years ago, very creatively named Robot 3. It was done at the time when I was just, I worked on as a PhD student, a little bit as a postdoc. This was a 24-degree of freedom cockroach. That was our version of the Cannon experiment. Our cockroach was slow enough you could just push it. So, but it's trying to maintain the same balance. There's actually, in this case, there was, what's going on here besides, there was a 24-degree freedom Lagrangian modeling that, but took into consideration, that's all done with pneumatic cylinders. And the pneumatic cylinders are trying to capture some compliance akin to muscle compliance. So if you saw it bouncing up and down like that, imagine if it was walking over a surface that was kind of shaking. That's a posture controller. Now imagine if you put a more complex controller with the legs to help it move forward. Okay, then we're capturing some of the balance, and then if we look at these electromechanical synergies, our chance of creating robots that can do that get a little bit better. And just to, so you know, I am not purely confined to insects. This is a stroke patient. Excuse me, stroke. This is a Parkinson's patient, okay? This is surgery done here on campus by a surgeon I work with, Dr. Deepika Narnambi. The video on the left is her just before her surgery. You could see she was tremoring before stroke. Deep is actually making, he's making a little mark on her head. He's going to do a keyhole surgery, and he's putting an electrode into the subthalamic nucleus of her brain, which is actually, if you draw a line between my two fingers, right there, the back, where they meet is about where he's putting in that electrode. And you can see pre-surgery, post-surgery. He gives her varying stimulus of voltage and amplitude as well as contact points. And so what's going on, again, when she was tremoring like that, it was a mechanical response because she couldn't control the stiffness of your muscles. If you're lying in bed at night, have your calf tighten up or something, you stiffen. You're not moving, but you're stiffening. Hence, that's critical to your control. That's modulated in the brain. So again, we're talking about the mechanical properties and how they're modulated by the nervous system. And that's fundamentally what I'm studying. So that's sort of the quick, high-level overview of the issues we're trying to explore. Where do we apply this? Well, biologically inspired robotics, robots like the cockroach I showed you. Trying to build balancing robots, bio-inspired mechanisms, looking at the synergy, and cybernetics, looking at devices that augment or support human beings in prosthetics or personal assistance or surgery. So I'll just give a few quick examples of these. This was one of the cockroach robots that I had built. We'd published this work in Bioinspiration, Biomedics, and the Journal of Robotics and Mechatronics. We patented the running gear on this robot and spun out a company on it as well. Again, this was a faster robot cockroach, but less complex than the one I showed earlier. It was able to handle many different kinds of terrain. Some years ago, actually, at a search and rescue conference, it was judged the most mobile robot in terms of being able to get through rubble after an earthquake. And we actually did an extension on that work. Those are just pictures on the right with the Singapore Ministry of Defense sponsored to make this an amphibious system. And that was all based on studying cockroach mechanics. This is a micro-robot. The robot is the size of an actual cockroach. That's it on the top left up there. That is next to an actual cockroach, so you can see its size. But my disclaimer on that, to be honest, I have to say that is next to the biggest cockroach in the world. That is Blabberus giganteus from Madagascar. So when it was built, that cockroach, so if a building was on fire, it was weighed about 300 grams. You would carry a bunch in your backpack, throw them out. In fact, we've designed a course here based on trying to make that robot autonomous with using microcontrollers. The robot crawled around. It could go over ground. It could climb over different obstacles. You'll see in a second it's pretty tough. It can fall down a flight of stairs. Now, if an insect had to go up those stairs, what might it do? Fly? Well, if it could fly. What if it couldn't fly? How about jump? That's a click beetle. It has a 4-inch vertical. I don't think I have a 4-inch vertical. So, muscles, again, they store and release energy. You stiffen them up, let go. That's how you jump. So this robot had a jumping mechanism where we studied how a spring could wind like that. Now that's the robot. The robot actually down on the bottom right was all the same principles I talked about with flying and balance walking apply with flying. That's a robot we call the Morphing Micro-Air Land Vehicle. There's a picture of it on the lower left. We studied some aspects of compliance in wings and bats and the same cockroach-like crawling, and what it led to, that was actually the first handheld micro-robot that could fixed wing that could fly, land, and crawl in a single sequence. It was the subject of a patent. Tokyo Broadcasting Systems and the Discovery Channel did specials on that robot. We published this work in Mechanisms and Machine Theory some time ago. The paper's been cited quite a bit. So that was for mobile robots. What about augmentation? Well, this is actually the work of one of my former PhD students who is now in the audience here. He's working at McLaren Applied Technologies, Tom Burton. That was an exoskeleton. By studying compliance in how people move, we can actually try to hopefully stabilize a stroke patient doing rehabilitation exercises. So the top right, you saw the patient trying to actually do these exercises without our exoskeleton and with it. That was Tom's PhD. Now on the lower left, this is a controller which I wish had preceded the exoskeleton. Unfortunately, projects don't always work out that way. So it's afterwards. That controller on the right is showing an adaptive impedance controller where essentially it's learning how to grip something that's trying to get away with it by modulating the impedance in the muscles. And that's a lot how you grip yourself. At some point in future work, I'm really hoping to fuse these. Again, ideally, the controller would have preceded the exoskeleton, but we probably didn't know enough to make the controller until Tom had built the exoskeleton. So I'm hoping to fuse both of those. But that simulation, you can see each trial, that device literally learns how an object is getting away from it. And we tried to mimic a lot of your own learning process in that. So this actually led to some further work in studying mechanical properties of muscles, where we actually developed a new interface to control prosthetic limbs. And my sound's okay. I will let this one play. Oops.
So at the moment, I'm controlling the hand through my muscles. So one on the right-hand side of my arm and one on the left-hand side. And I believe it's all through murmurs. And it's a very slight movement to open the hand and close it. What's interesting about the technology is that it's far easier than my current myoelectric prosthesis, which is a more aggressive use of my muscles, which tires them very quickly, which then makes it untenable for using it for long periods of time. So at the moment...
So that's a gentleman, his name's Alex Lewis. He's been working with us for about 2.5 years now. We actually looked at, this is a new sensor we have developed that actually studies essentially the mechanical output of muscle when it moves, as opposed to the electrical output, electromyography that most people, it's called mechanomyography. We certainly aren't the first people to explore the phenomenon, but we have applied for a patent specifically on this sensor, and we published this work in IEEE Transactions on Mechatronics. And again, looking at sort of the, how in studying the body move and the mechanical properties changing the muscle, it led to studying this kind of sensors. We're actually in the process of spinning out a company right now based on that for prosthetics. So where I'm hoping this will scale up to, we've got some pilot experiments that now is essentially what we talked about was how mechanical properties in the body change. We need to know that in order to build robotic augmentation mechanisms, which is really the main focus of our work. We still have some projects going on in mobile robots, but a lot of that was showing more in history what led us to this point. We've got 2 projects going on with the medical school at the University of Oxford right now. We're working with patients with implants in their brain from Parkinson's, where we're trying to look at how the signals inside the brain modulate based on the ability to control oneself. We published our first paper on that in the Journal of Neural Engineering, which was kind of exciting because it was the first time someone had taken signals from that part of the brain and correlated it to both left and right hand movement. But the larger vision where I hope to go towards is taking the implants in the brain there, looking at that output, looking at some surface measurements like the muscle measurement I measured, and tying that all together to, say, an exoskeleton, where that exoskeleton will adapt to your body as it moves based on signals within it. That's where I'm hoping the work will scale up to in the next several years. So I'll talk very briefly about our translation, some of our translational activities that are going on right now. This is not necessarily tied with the larger vision I meant with Risha, but some of the stuff has reached maturity where it can be looking at translation. OSER, it's one of the largest manufacturers of prosthetics in the world, is sponsoring us for using our sensors to control prosthetic legs, which is being shown in the lower left. There's a new my PhD student of mine, his name is Sam Wilson, is as of about a week ago has spun out a company called Surge Technology, where he's trying to actually, and Alex, the gentleman who's showing there, is one of the principals in that company, where they're trying to actually create a new prosthetic limb interface. And McLaren Applied Technology is working with us on exoskeletons and using these sensors to monitor balance, which I hope will translate. This also led into a little bit of a sideline project where this was something that really spun out of the motion tracking work we were doing. We made smart boxing gloves, which I'm demonstrating them up in the top left. That actually came about because we have a student on the Imperial boxing team who found out I used to amateur box, who to this day won't tell me how he found out. But he kept hounding me to come box with the Imperial team with him, to which I said, what part of your 20 and I'm 40 isn't clear to you? But at some point he did get me out there and we started correcting his strokes, and I introduced him to our stroke rehabilitation work we were tracking. That's him, his name is Charlie. And he made these smart boxing gloves. You can tell every punch he's thrown is tracked. He spun out a company. These went for sale in October. About 1,000 have been sold. Bottom center, I don't know if I have any boxing fans. That's world heavyweight champion Anthony Joshua, who's pictured with our team. Top right, actually, is another student on the Imperial tennis team who has done something similar. Her name is Disha Panchal. She's actually made a smart tennis tracking system, and you can see each stroke she has is being tracked there. We're actually talking with investors right now about possibly having a new spin-out company for that as well. And finally, there's because of the brain-robot interface we're working with a company called Emotix, which has released a domestic robot. It's called Miko. That's it right there. It stands for My Companion. It's a domestic social robot that's actually supposed to work with children. It helps with homework, reminds them of soccer practice, things like that. That is for sale right now. So it's been an exciting time to feel. I'll close just by saying a few things about our external impact. We were invited to present at 10 Downing Street, few best papers, few featured speaking. But I think the most exciting thing was, as a field, I believe robotics has really overpromised itself for quite some time. Certainly, I finished my PhD several years ago. I was told by 2019, if I gave a talk like this, a robot would be getting me a pint of beer while I spoke. I don't see the robot. So it is nice to see actually some 5 spin-out companies, a few press that's really getting out in the press. So I'll close. Future work, I want to do more modeling of neural interfaces. I really want to explore, because I think the damping properties in muscles are really underrepresented in terms of how we balance, and I want to know how that's modulated with the nervous system. I hope the implants will help that. I want to look more at impedance analysis so that stiffness modulation can be taken to exoskeletons. I'm very excited about some new work in looking at data fusion for smart environments, smart homes, smart workplaces, maybe even smart cities that can give an external context to a piece of assistive technology. And we're starting to broach some work in teleoperation too. So the same way that we saw the amputee controlling a prosthetic hand, you could potentially remote control a robot that would be fixing, disarming a bomb or fixing a pipe underwater. So with that, I'll close. On campus, I'm certainly not doing this work alone. Professor Alison McGregor is my closest medical colleague. Deepka Narnandi, I don't drill holes in people's heads. That's him doing that. So who else I should mention? Roger Quinn's my PhD advisor, and Roy Ritzman, who I worked under for my PhD, where I don't do work specifically with cockroaches, so they're the ones who are doing that. And the group at Oxford, Peter Brown and Tipu Aziz in Wheeling-Tan, they're the ones who are working with us in implants in Oxford. Certainly my research group, I should mention, we've got 14 people, group postdocs and PhD students, who I'm very, very fortunate to be lifted by. So, and of course, who's paying the bills? We can't live without them. So, thanks for your time. I think we are pretty much out of time, so I'm happy to take questions, but maybe it's best if we do that outside.
Outside, which are hopeful the cockroach free, and they are either outside or down the stairs. I'm not sure where they put them. But we reassemble here at the top of the floor. There are posters in the room opposite. So, welcome back after the break, everybody, and a warm welcome to those of you who weren't here before the break, particularly to our industrial visitors, of whom there are many in the audience, I'm pleased to say. So, welcome to you all, and I'll repeat my apology about us being in this building rather than in our building. This was because we got bumped by the president, whose office had failed to book the lecture theatre, so we booked it and then got bumped. So that's why we're over here. Anyway, it's my great pleasure to introduce Barbara Lane. Barbara is a fellow at Arup. She comes from Dublin, as you will hear, and she did a bachelor's in civil engineering in Dublin and did a PhD in fire engineering at Edinburgh. She's a fellow of the Royal Academy of Engineering. She's won a Royal Academy of Engineering's silver medal, so great honours both. And she was also a member of an expert witness for the Grenfell inquiry. So she's exceptionally well qualified to talk about fire. So Barbara, we look forward to hearing your talk.
Thank you. Okay, well, thanks to everybody for taking the time to come here for my presentation and for Imperial's very kind invitation. My name is Barbara, and I'm what's called a chartered fire safety engineer, and I work at Arup. I've worked on fire safety problems and solutions in all different forms in buildings, in concept stage, design, construction, and building in new stages for projects all around the world. And more recently, I've been acting as an expert witness on various disputes regarding construction quality, and I'm currently spending all my full-time project time in Arup as a fire safety expert witness to the Grenfell Tower inquiry. Now, I know Imperial were very keen that I'd speak a lot about Grenfell, but it's not very appropriate actually at the moment. But I am going to just talk about it briefly here. Throughout my career, but particularly since I attended the scene of the fire, and most particularly after what I saw and smelt the Friday morning after the fire, I've been analysing and worrying and questioning and pondering the issue of how one creates a fire-safe world. There are no words possible to describe the carnage that morning, and it was a carnage that was witnessed by a very small group of people, expert in disaster recovery, with a few people like me present with no prior experience or understanding of what utter carnage truly entails. It was and remains so, nothing compared to the carnage experienced by the residents of the tower, their family and friends during the fire. These are cold, hard facts, and they are not some to be disparaged emotions. And this was central London in 2017. So it's really not possible, in my opinion, to agree that a simple return to the so-called business as usual model is acceptable after such an event. Okay, so I'm clear that to create a fire-safe world is an exceptionally complex problem, hence my use of the word conundrum. But I'm equally clear it requires a solution. Despite all my own experiences and the experience and skill of all of those people around me, we've not been able to easily reach for some swift resolution for the state of safety in our built environment as we find it today. I'm also clear, and I don't believe I'm alone in this, that it is time for some positive, proactive, honest and collaborative behaviour and action to enable a transformation out of unclear and uncertain complexity and into a more systemic, resilient and effective means of creating a safe built environment. The fire safety conundrum, I've come to believe, isn't even simply a fire safety science and engineering problem. And I want to try and explain what I mean by this today. Fire has been a source of light, comfort, and heat to humankind throughout the ages. It's a familiar process, and for the arsonist in all of us, it can even form a pleasurable part of our leisure time. It can also be powerful, uncontrollable, and dramatic in effect and consequences. This is a movie of a fire in an Arup building. The force and scale is breathtaking. And of course, the sounds of ever familiar measures to protect us are always in the background of day-to-day life. The impact of fire is part of our shared history, part of folklore, part of society. How people and property are protected from the complex phenomenon of fire has a long history. Here in the UK, our regulations stem from the consequences of the Great Fire of London in 1666. This was a time when this city was built with timber, which burnt unnecessarily, disproportionately, with apparently very low loss of life, but significant consequences for the city itself. When this fire happened, there was no fire brigade, nor any rules for building safely. After this fire, change was slow, but then insurance companies provided firefighting. The city was divided into areas, each with a fire watch in place. New rules were created for constructing buildings and streets. Since that event, and almost consistently until recent times, a cornerstone of building fire safety was to rely on non-combustible materials. This is very useful historical context now. But that was then, and this is now. There are conflicting demands of the built environment in these times. In the last 25 years, cities have grown larger and more quickly than ever before. Fishing villages have become megacities. Deserts have become urban playgrounds. By the middle of this century, 75% of the world's population will live in cities. Cities occupy less than 1% of global land, but generate over 2/3 of the world's economic output. Modern methods of construction are rapidly evolving in response to this increasing urbanization. The rate of urbanization is huge. 2.5 billion more people will be living in cities by 2050. But signs of looming problems have been emerging. The Lacrosse building, situated in Melbourne, is a 23-storey mixed-use building and had a fire on the morning of the 25th of November 2014. In the words of the municipal building surveyor, he said, "The fire at the Lacrosse building is a first in Melbourne in that it directly affected approximately 450 to 500 people who required immediate evacuation and accommodation." He added, "The fire spread vertically and was not contained in the room or area of fire origin. Fortunately, in this instance, there were no fatalities or serious injuries." Then another notable fire at the Address Downtown Hotel near the centre of Dubai, New Year's Eve 2015. This time the fire started on a 20th floor terrace of a 63-storey hotel. About 1/4 of the facade was consumed by the fire. The fire spread in all directions, and this was ACP cladding. Modern methods of building construction relying on combustible materials were now under scrutiny and of rising concern. It was acknowledged in some quarters at that time that there were hundreds of buildings in the UAE and hundreds of buildings in Australia, respectively, cladded with similar materials. So on the basis of hundreds of buildings having been constructed in this way, I will speak about the scale of the problem in the UK later, we were and are now dealing with a fire safety problem not from an individual building perspective, but at an entirely different scale. I use the phrase city scale. By this I mean large portfolios of existing buildings that require attention now, coupled with an increasing demand for new buildings and associated new critical infrastructure. But urbanization is also changing cities in another way too. There is 1 billion people who live in informal settlements around the globe. 33% of city dwellers live in slums. Fire is one of the primary threats in these informal settlements too, as kerosene lamps typically act as a source of heat and light. This image shows here what happens 1 hour after a lamp has fallen over. Fire in an informal settlement can affect thousands of people, as well as loss of life. The consequences of fire include serious injury, destruction of homes and property, and short and long-term impact on livelihood. Therefore, recovery from fire is a long and difficult process. This is particularly exacerbated in informal settlements, where a lack of insurance, financial instability, and insecure tenure are common. One must also consider the approximately 25 million people living in refugee camps, another consequence of the shifting world. These people also live without adequate fire protection. The scale of these fires is caused by non-existent access routes, scarce water provision, the materials used to construct the shelters. These are matters of city-scale planning and consequential effects. It requires expertise from disciplines of so many forms to tackle the multifaceted problem created by the scale of issues facing cities. These are issues substantially remote from the typical perception of what a fire safety scientist or engineer does, and also remote from the scale of problem the fire safety profession is typically associated with solving. A final contributing factor to increasing urbanization is to do with migration, with 258 million international migrants recorded at the end of 2017. But there's another factor impacting the built environment, and this is climate change. This too is also becoming relevant to fire safety in the built environment due to the increase in the number of fires in the wildland-urban interface. The wildland-urban interface includes locations where urbanization meets the natural environment and where communities build homes in areas of forest, for example. The recorded evidence shows the increasing area of wildland fires year on year. This includes this country. Climate change is creating the conditions for wildland fires. The risk of human-caused ignition is increased in wildland-urban interfaces and therefore increasing the frequency of unintended fires. The consequences of fire at this interface includes impact on life, livelihoods, environment, and agriculture. But ultimately, what all of this means is that fire causes 130,000 deaths annually. Fire-related burns cause 5% of all injury-related deaths globally. In comparison, war accounts for 2%. In 2016, approximately 1/5 of the world's population from low to middle socio-demographic index countries, but half of the world's deaths due to fire occurred in those countries. The impact of regulation to improve the energy performance of buildings has also driven the rise of modern methods of construction, particularly those with highly insulating polymeric insulation foam, and further mass timber elements are increasing in popularity substantially. There is pressure on the construction industry and the stakeholders in the wider built environment to stay on that journey of limiting our impact on the built environment, and a strong drive to achieve sustainable development. This is development that meets the needs of the current generation without compromising the needs of future generations. What all of this creates is something very far away from a single building and its fire safety solution. Instead, we have transitioned into a complex system containing multiple buildings with fire safety problems, a strong demand for ever-increasing numbers of new buildings, interfacing with infrastructure, interfacing with wildland, and for some places, the presence of informal settlements. But I have one final reflection on this complex system. The very purpose of buildings are changing. There is an increasingly flexible definition of workspace, of living space. The recent Ocado fire in Hampshire adds an interesting dimension, and I don't have any special insider knowledge here, just to be clear. This is a large factory space devoid of human occupation, occupied instead by robots, apparently fully fire protected. But once the fire started, human intervention was required, interfacing robotic operations and human firefighting. The Ocado share company price dropped. They had invested in this operational process and technology, and we're apparently selling it to others. What does it mean for that technology, that operational approach, when it interfaces with a fire? If it is true, and I've no factual evidence yet, that the fire started in the robot, now we have an absolutely fascinating fire scenario and resulting building condition, and resulting operational failure, and resulting property loss. What a complex problem to try and unravel. There's only going to be more building types like this, not less, as the digital transformation of the built environment continues. What this all shows is the side effects of rapid urbanization and rapid advances in new technology are piercing through the built environment and making some spectacular demands of those who create it. I don't know about all of you, but I find these very profound matters, and they feel very far away from ad hoc fire safety research or a register of chartered fire safety engineers or a knee-jerk regulation change after one disaster or another. We need something far more substantial, such as a common definition of objectives to help us all achieve clearly defined safety goals. I've set out some of my suggestions here. Complex systems thinking is therefore required to understand the direct and indirect consequences of fire in order to prioritize investment in fire risk reduction. Closer to home, let us now ask ourselves if our current safety system is working. The answer is a very large and loud no from me. The government have confirmed a total of 474 buildings in England clad in unsafe materials. The most recent public statistics show 72% of public buildings with unsafe cladding are undergoing some form of remedial work. But this figure drops to 8% for private buildings. The current statistics mean 26,500 homes in England are currently clad with similar cladding material to Grenfell. This means 20 months after the start of the building safety programme, more than half of the total number of identified buildings have had no remedial works done on site at all. What we need is a building safety programme for these properties in England where the works are prioritised as a function of risk to life. What we also need is a high-performing system that can produce safe places to live and work and which protect our infrastructure and our communities. So now I want to turn to some potential solutions or methods to achieve solutions. This is a work in progress, but I hope the themes I present today might provoke some discussion and consideration and become cornerstones of a wider concerted plan for change. Producing a safer world is clearly a multifaceted problem. What are the cornerstones in this multifaceted system that can create or cause or contribute to a system which will produce effective, resilient, fire-safe spaces? Today, I just want to try and focus on three, which I've classified as scale, fair and honourable dealings, and digital transformation. So first to scale. There is a substantial need for an increased understanding of the number of stakeholders and technical disciplines needed when creating something in the built environment. There is a scale of integration across the technical disciplines and stakeholders needed in terms of a common understanding and commitment to solving the fire safety problem. There is a substantial scaling up needed of skill. Fire safety knowledge cannot carry on being a niche discipline area. There is a substantial scaling up of a core group of experts, yes, but also a substantial scaling up of education across the wider disciplines involved in the built environment. Everyone from the architect, the mechanical engineer, the contractor, the firefighter, statutory authorities, product manufacturers and suppliers, the government itself, regulatory bodies. There's such a long list. There is also a substantial change needed in the wider context understanding of either expert fire safety scientists and engineers, as well as from all the other disciplines and parties involved. We cannot carry on producing graduates or apprentices who think about fire in such a narrow niche way, or not even as relevant to them at all. Truly interdisciplinary thinking and considering fire safety at the scale it is impacting our cities and the built environment is key. This requires commitment to an education system at the scale needed, along with wider strategic thinking and understanding, coupled with a more extensive expert capacity. There is a need for a totally different scale of investment in research. This needs to be at a scale that brings fire safety science out of its niche domain. It needs to be at mainstream scale. We also need a shift in emphasis from pet projects or ad hoc projects at universities or other institutions towards an effective and organized applied research plan. We in industry have some serious problems, and we need rapid assistance to solve some very practical and immediate problems. We need interdisciplinary effort. The next cornerstone, I'm assigning the title Fair and Honourable Dealings. This is the complex part of the change needed, in my opinion. This revolves around behaviour, agreeing levels of acceptable risk in our communities, and actually valuing safety, being prepared to pay for safety measures, but coupled with being honest about what are relevant safety measures. I'm not a fan of change for change's sake if it doesn't in reality actually improve safety standards for the community. So some suggestions. We need a common definition of acceptable risk in order to understand and plan for the consequences. As a profession and as a society, we are not agreed on acceptable risk, and there has been a trend, therefore, not to plan for related consequences. We need transparency regarding performance requirements and acceptable solutions from our regulations, from our statutory guidance, from the materials and products relied upon to create safe buildings and spaces. We need honesty about grey areas and proactive engagement to resolve them, and accepting this is a dynamic situation that requires regular review. This requires government, industry, and academia commitment. It means considering the impact of our thinking and decision-making on the community rather than on the bottom line. There is a stark need for more robust construction materials and construction systems to create our safer built environment. Determining the fire performance of products and systems, the detailing needed to ensure a resilient response in real fires is also complex. There is a lot of scientific effort needed to urgently assist industry in this. There is an acknowledgement now of an industry-wide problem here, as communicated in the Hackett Review and the publicised data from the Grenfell inquiry. We need also an inclusive environment regarding fire safety expertise. This is a hugely political arena and not appropriate for me to go into detail here. But from my current perspective as a designer, there are issues around the need for the fair compensation of technical services, incorporating firefighting requirements more robustly into design and construction standards, the provision of equipment and education suited to operating in the modern built environment, being an industry that proactively deals with those needs through design and construction processes, industry demanding rigorous enforcement of standards, and industry placing safety at the heart of the works they are providing for the community. And finally, valuing safety. Being an industry and a government, aided by academia, by the way, in being prepared to invest in robust and appropriate safety measures. Who is going to lead this change agenda? The last proposed cornerstone for today is to do with investing in the benefits of digital transformation to help us create a safer world for our communities. The more I understand the power of digital buildings and digital technologies, I see opportunities for being able to gather and analyze data at scale, relying on techniques such as what is termed user experience to create a different caliber of smart building for communities and for firefighters. Being able to rely on sensors in buildings to drastically improve maintenance regimes of fire safety systems, or to provide real-time data for emergency preparations and live emergency decision-making. Finally, having a common source of information about a building for long-term quality assurance, maintenance, and understanding. Digital transformation and its role in improving the built environment is such an exciting subject in itself, even if it means learning about cockroaches, I learned today. There are plenty more cornerstones to define and decipher yet. For this world-class university, there is a huge role for you in shaping and leading the transformation of the built environment. I am inspired now, all the time, by the young people entering our technical disciplines because of their refreshing commitment to change and their high demand for honesty and fairness. This particular little problem is down to you to sort out. Thank you very much.
Thank you, Barbara. We've got plenty of time for questions. Can I ask you to identify yourself if you have a question, please? Yeah.
Just goes to Imperial College.
Hi.
Thank you, Barbara. Really interesting talk. I had a question. Since it's such a multidisciplinary field, how do we move fire safety science out of the niche that it's currently in?
Well, I think I was trying to hint at a little bit more organisation. So I think the first step is accepting that fire safety isn't something kind of either too familiar to think about or so expert that you can't get involved. So I'm trying to make it something that it feels very relevant to everyone. And so it becomes part of the education of, far more disciplines, say, than the so-called classic fire safety engineer. And then as well as education, research and other things, and that investment in those subjects is at a more orchestrated and organised level and at the scale we need. Because we've just been a certain size for such a long time, and that's clearly not having the impact that we require in our communities. There are some people who can make decisions to make that different, in my opinion.
Other questions?
Hello, Matthew Bonham from Imperial College. That was a great talk, thank you very much. I was curious about, again, also talking about unifying these fire safety problems with the larger community. I was wondering, what do you think are the largest barriers in the way of doing that right now? Like, what is stopping people doing it already? Why haven't people done it?
I think as a profession, so say both in industry and academia, I think we're quite protective of what we are individually doing. And I think there's just a new level of openness needed to help us start to try and look out and see who else we should be working with. Because if you take smart buildings, we actually need so many people who can do that weird cockroach stuff that I can't even describe. But I know that technology and that skill and that numerical ability is the kind of thing I need to be working with from now on. If I'm going to do something totally different in a building, it can be applied into, say, the construction industry. So there just seems to be a mind shift needed in who we should be working with, and then who else is relevant to safety.
I've always had the feeling that the construction industry lags behind other industries in terms of adoption of innovative solutions, innovative technology. You talk there about the use of smart buildings and advanced technologies. If you compare it to the technology industry, but even oil, chemical, what's going on there? Do you think? Is it because the consequences are perceptibly less, or is there something intrinsic to the built environment?
I can say a few things there. I have not been able to answer that question, and I've genuinely been thinking about it, because even in Arup now, when we bring in new technology people, just the way they behave and what they expect. They have this thing about failing fast. So you try out something, you fail, if it doesn't work, you fail fast, you try something new, okay? It's this attitude where you're very open about what's working, what's not working. Just even having that kind of attitude in the construction industry, can you imagine that, even on the most simple things? And I think we seem to have become the most old-fashioned grouping. I don't know, I was trying to touch on fair reward for technical services as well. I just don't know if there's something about it's not valued, if it isn't understood. It seems to be a curious mixture of the two. But we are way behind where we could be if we chose to make that decision to place safety and other things at the heart of what we're actually doing when we carry out a construction project. Because we are all in construction in the end. And I think that's another little problem that we might have, that some of us don't understand that everything has to get built one day, and understanding how that is done properly must happen much earlier in the process too. So I haven't cracked that one, but it kind of can't carry on anymore. That's what I'm clear on.
Thank you very much for your talk. I have a question. So we can see that nowadays more and more fire safety regulations are applied for new buildings. But are there any approaches for old buildings that were built in, for example, as Grenfell in 80s or even earlier? Are there any measures to prevent the fire spread in old buildings?
Did you say there's more and more fire safety regulations?
They are more and more applicable for new buildings. Yeah. So when the building is constructed, it's already applied there, but it was not like this decades ago.
I don't agree that there's more and more fire safety regulations for new buildings, but I'm just being a bit pedantic. I understand your point. The issue of how existing buildings are dealt with, let's say, by law and regulation in this country, I can't tell you what I think, because I'm in the middle of doing that for the Grenfell inquiry at the moment. But there is something about having a very large existing building stock and understanding its intrinsic level of safety at this time and making a decision, yes, about what we're going to do about that. You can read my 1,000 pages on the material alteration clause in the building regs another time. Yeah.
You introduced Byron Tucker from Tata Steel.
Hello.
Hi. You introduced this as a global problem. I can understand it's a global problem, but can you see any world best practice that we should be adopting?
Yeah, I was trying to say it was to try and think beyond. I think in fire engineering we think about the building we're working on. I'm trying to get people to think a little bit more big picture. I think there are some other countries, yes, that have different rules about how certain materials are used, yes. And I know that from some of the countries I've worked in. So for example, how some of the codes in the States consider fire resistance or what should be in an external envelope are somewhat different to what we may have thought was acceptable here. So there is different standards and there are samples of best practice in other places. We'd have to pick a specific subject. I can't think of one country that's substantially better at everything we need at the moment. Is that okay? I think there's pieces from all different places. And some countries are slightly ahead of us because of their own problems as well, as you know, in Australia and other places. Is that okay? Yeah.
There was a fire not far away from here at the Mandarin Hotel up in Knightsbridge. It was a recent renovation. It's a first-class operator. It's the Mandarin Hotels. It's a prime owner. And the hotel had to shut down, but it was right after the renovation phase. How would you explain that an incident of this level can happen, given that they already have the permits and everything else, given that you're closer to the subject?
Yeah, but I don't know what was happening in that hotel with respect to its maintenance regime and its fire prevention regime. So, I mean, I would just be entirely speculating if I was to say something. I try not to do that. So there will be something about what caused the fire there and how it spread. I don't have any information at all.
You're standing on the shoulders of Arup, who I'm paraphrasing him, if quantity surveyors got interested in aesthetics and architects got interested in cranes, we'd be getting somewhere.
Yeah.
So you're kind of saying if fire engineers get interested in construction and architects get interested in fire, we're getting somewhere.
Yeah.
But the poster out there, in Guillermo's poster, basically says...
What's on the poster? Yeah. Guillermo, what's on the poster?
Oh, the posters. Oh, sorry, I totally misunderstood. Yeah.
Oh, you mean technical work being presented across the hall? Yeah.
It basically says that architects don't know how to build fire safety.
Who wrote that down? Which hold up your hand and answer Ian's question, because I'm not. Yeah. Is that written on a poster in the room across the hall? That architects don't know what they're doing? Yeah, I don't agree that architects don't know what they're doing. I think that's a very rude thing to say. And I don't like when they say fire safety engineers don't know what they're doing. I think it would be much better if we had a much more respectful understanding of what we all need to do to a very minute level of detail, actually, to create a safe building.
It's kind of strange, really.
Well, I'll go rush over and read who wrote the sentence and suitably admonish them later. But I'm sure they were trying to be helpful and apply for more research funding for their work. Yeah.
It's a game of windows, isn't it?
What's a game of windows?
It's got to be a game of fenestration, as it used to be in the fire grading reports after the Second World War.
Other questions?
From Imperial College. Thank you, Barbara, for such an amazing talk. I was curious about, you talk about forest fires and informal settlements. How does Arup approach the fire safety engineering of these problems?
Okay. Well, we are very clear that we don't know enough at all about forest fires or wildland fires, so we're trying to get some skill and expertise there. So we don't do that at the moment. And then for informal settlements, I think you know, well, Danielle is here actually, she and others in Arup have been working very hard with all different types of communities and stakeholders in that area to try and help them understand some fire safety goals and objectives. So Arup and Danielle, who's here, are trying to enter into that area and work out what kind of practical things that we can do. But that's a new thing as well. Yeah. Hello, cockroach person. Yeah.
Hi.
We need to have a chance, by the way. Yeah.
I'm Ravi Vaidyanathan from Imperial College. Actually, it was just a bit of a follow-up on the question that was just asked. When you said we don't know very much about forest wildfires, is it even possible to characterize what we don't know? What are maybe the major issues that we need more information on?
Do you want me to do that? So I'm not an expert in wildland fires, and I never will be because I'm too obsessed with buildings. But there are bodies of research work, and some of them work with you, bodies of people who are getting into the parameters and lists of problems that need to be solved. I don't like to kind of make up answers when I'm not an expert in an area, so I can't be more specific. But Guillermo there, do you see him? He works with you. He knows all about it.
You seem to be saying that there's a conflict between the desire for better insulation in order to help combat climate change, and a tendency there, particularly retrofitting, and then a tendency to reduce fire safety. Is there a way around this one?
Yeah, like, so I think maybe there might have been a bit of a rush to satisfy one driver without carefully thinking about consequences, so in this case for fire safety. And it can't be that we just give up on energy performance of buildings and rush off to think about a single driving parameter now, which is fire safety. It's about the careful consideration of both. And there is a way of using polymeric insulation safely. It just has to be thought about properly and detailed up and installed properly in a building. So it's about the careful consideration of, of conflicting risks, if you will, or conflicting drivers.
You earlier said that the construction industry should drive to be like more flexible or take on more new technologies faster, and that they mainly don't do it because they're afraid of failing quickly. Do you think there's enough, in some sense, enough economic incentive for the construction industry to fail because we can build buildings already so they do their purpose of the, and also can we afford to fail in the construction industry, because failing in, for example, in technology and for a mobile phone, for a laptop or other things is relative, they're not really big consequences, but failing is more similar to what would happen in the aviation industry.
Well, I was imagining failing in a theoretical sense, so if you're doing fire testing or trialing or something numerical or having some kind of innovative thing you're trying to work through, that's the type of, I was talking about how new technology companies are interested in being honest about failing fast. One might say that we actually are failing in the construction industry at the moment, because we do seem to have a rather long list of problems that now need to be resolved in our existing buildings. And so we need to work out how to solve them and work out how not to create another generation of buildings with some, intrinsically unsafe construction methods.
Better labelling of materials, because for a personal story, my daughter was buying a flat in Greenwich, Enderby Wharf, and
what wharf?
Enderby Wharf, the Barrett's development along the Greenwich Peninsula.
Is that one of the buildings with the unsafe cladding on it?
She did it. But I asked the Barrett's people, I said, well, how do I know that's safe or not safe? And they said, oh, we've used all the current regulations, we've built according to the rules, it's safe. But I said, how by looking at it can I tell it's safe? And it's not, you can't. So is there more scope for some sort of better labelling of materials on the outside of the building?
Exactly. With these new technologies, having some kind of common platform, like a digital platform, where you can literally check the materials, what are they called, what do they do, in some kind of digital replication. We've been talking about it for such a long time. It's still not really happening. There must be someone very clever who can do that very quickly, and then you'll actually know. I would ask, though, how do they know they complied with all the regulations when they built their building? But we'll leave that one there. Yeah, I'd love to hear about that. Yeah, no, but it'd be nice if they answered it properly, wouldn't it? And they gave you some competent evidence other than a single sentence. That's what they should have done for you.
You seem to say how much of you think of a perfect solution is how much policy change is required compared to engineering knowledge change. Because I think you seem to say, it seems to me that we know a lot about how to build safely, but it's not necessarily being implemented. And the implementation is down to regulations or things not being followed or other things. And there seems to be a need to change the policies or how people behave to do this. And how much do you think is it engineering not being applied or things not being available compared to we need to change the way how we do things?
So I won't assign any percentage responsibilities at the moment, okay? but I hope I made it clear that I think it's a two-way thing. So we need educated government, educated regulators. When I say educate, I'm talking about fire safety, not in a kind of a disparaging way. They understand fire safety, okay? The government, the regulators, the policy makers have to understand better the consequences of decisions made, don't they? So if they change rules for energy, we have a duty to understand other consequences. And then that equally applies to the parties who are trying to comply with those rules and the decisions they make. So I'm not prepared to say, you know, if there's some kind of horrible out of balance. At the moment, I'm prepared to say there's an equal level of change required very, very quickly, not in 1 or 2 generations.
You said at one point, I think, that we need to agree on what's an acceptable level of risk. And I just wondered if we could unpick that a little bit. Because it seems to me that that's actually a very difficult thing to achieve. As individuals, we each have different ideas of what's an acceptable level of risk, and also we're entirely inconsistent about the levels of risk that we will accept in different circumstances. So how can we define an acceptable level of risk, and therefore how can we determine what's the correct level of resource to allocate to fire safety vis-a-vis anything else?
So I agree with all the points you've made. I would like to understand, say, if one took the current regulations, or let's say the decision by government to allow people to carry on living in the buildings with the unsafe cladding, how it's been quantified, what the risk to life is. There are techniques for doing that, well-trodden techniques, and what the consequences are as a result of that risk. And I think there are very formal, well-evidenced methods to do that. And I would like to start introducing that much more explicitly into our designs. I have control over design, and ideally into guidance or regulation coming out towards designers. There are technical ways of doing that.
Of course, but
yeah.
For instance, I mean, if you take something like a Hatfield rail crash, for example, what was done after that was to place speed restrictions all the way across the network until they had replaced all the rails which were susceptible to gauge corner cracking. Now, one can almost certainly do a calculation which says these are the number of people who were killed in car accidents as a result of the increased car traffic, as a result of those restrictions on the network. So it wasn't, as it were, a logical calculation based on that kind of risk analysis. It could have been, but it would have been unacceptable to the press. And it would have been unacceptable, the politicians wouldn't have allowed that risk to be carried, because if there'd been another train accident, their heads would have been on the
But I think you kind of answered your own question, thankfully, so I don't need to... No, I'm very relieved, because don't we have the same problem, okay, now? Because I would like to know who's done a risk and consequence assessment of even, say, the public building stock, or not. I would like to know.
Is there more room for a stronger regulation of the building sector, like the FAA? Someone that could really step in.
I'm a fan of that, but I think I'm in the opposite kind of political, I think that's very political now, isn't it? Personally, I would like clearer, goals and objectives, so then you can do more explicit or complex or clearer solutions to well-defined goals. But I'm not in charge.
Time for one more question?
Yay. Okay, thank you.
Yeah.
John Sargent, I used to work for Castrol.
You used to work for who?
Castrol.
Oh, yeah.
Great move for Katie.
Yeah.
I just wondered whether you think there would be any impacts on fire safety, depending on the outcome of the current discussions in Parliament on Brexit?
I mean, it's like my dad came, so it gave me the opportunity to say I'm an Irish European passport holder about to be deported from this country. So what do you think I think about fire safety and Brexit? I'm not answering that question. Yeah. Yeah. But I have started speaking in Irish more recently, I will say that. Yeah. Okay, thanks very much.
Posters again in the room. Thank you for coming.